Welcome back to Larry's Classroom. As an electrician or electronics technician, you're going to need to take in measurements and you're going to need to use meters. So we're going to do a little talk about meters today. And first thing we're going to talk about the meter movement, which is the heart of the meter. And we're going to talk about what's called a moving coil meter. In a moving coil meter, you'll have a magnetic part that probably be a permanent magnet, and inside that thing there'll be a little form. We'll try to draw a little form here that will pivot on a pivot, and there will be wires wrapped around that, and those wires will come out to the terminals. And there's also, I'm not going to draw it in here because I would clutter things up quite a bit, but there's a spring very much like the hairspring in a watch that this thing wraps against as it turns. And there's your needle. And when we put current through that coil, it creates a torque that moves and wraps against this spring. So this gives us an indication on the scale of the meter as to how much current is going through that meter. And that current, or that movement, will be proportional to the amount of current. If the meter was designed so it took 1 milliamp to run it all the way over here to full scale, if you had half a milliamp flowing through that meter movement, you would have a half scale deflection of the needle. Now the moving coil meter, a very sensitive version of it is called the galvanometer, and it's also often referred to as a d'Arsneval movement, which is named after the man who invented it, which was actually invented in 1881. So I'm going to write that name down here just for you to see it. D'Arsneval movement. And invented in 1881. That's when he got a patent on this thing. Now there are things that characteristics of this meter that are important. One of which is called IM. Current of the meter, which is the amount of current that's required through this little coil to create a full scale deflection. Yeah. And there's another characteristic called RM, which is the resistance of the meter. Resistance of the meter, which is basically the resistance of the coil wire. And these meters come in many different full-scale deflection values, and as you go to lesser and lesser current required to pull it to full scale, it's because they put more turns of a very fine wire and possibly change the spring rate of the little spring in there too, but the resistance tends to go up. So we're going to talk about IM, typical. So typical IM, if you got a 30 milliamp meter movement, so it'd be a meter that took 30 milliamps through this little coil inside of it to push it all the way over to the full deflection, is probably 1.2 ohms or less. When the IM is in the area of the 1 milliamp, which that's a lot less current to run it up, we see that the resistance of the meter goes up, and we might be in the 50 ohm range or so. And an even more sensitive meter with an IM of 50 microamps, and that's 50 millionths of an amp. This is 1 milliamp, which is 1/1000th of an amp, so this would be that would be like 1,000 microamps. So this would be like a range of 20. This is 30 times more sensitive. This is 20 times more sensitive. So that's going to have resistances in the area of 2,000 ohms. So your resistance of the coil in this meter movement, as your meter becomes more and more sensitive, taking less current, ends up being a greater resistance of the meter movement itself, which is primarily because it takes more turns of wire to generate the torque to get that to do what you desire to do. Now, we'll talk a little bit about making current measurements. We're going to talk about voltage measurements eventually too, but mostly we're going to talk about current measurements today. If we try to do a current measurement, our meter is in series with the rest of the circuit. So we're going to do a little bit of an example here. We're going to put a 75 volt power supply. We're going to put a few resistors in series in this circuit. Now, each is R1. In this case, is 250 ohms. R2, 250 ohms. And R3 is also a 250 ohm resistor. Now, we can use Ohm's law. We can calculate the current here. We have current I equals voltage over resistance, and here we have 75 volts, and our resistance is 750 ohms, which if we divide that out, that comes to 0.1 amps, or we call that 100 milliamps. So we're going to have a current here of I equal to 100 milliamps. Now, if we want to measure that current, we have to break the circuit and put the meter inside there. So if we put a meter in here designed to measure 100 milliamps, and this is a 100 milliamp meter designed for 100 milliamps, we connect it in just like that. Now, we were talking a little bit ago about the resistance of a meter. The 100 milliamp meter is probably going to be, less than 1 ohm. The 30 milliamp meter we found to be about 1.2 ohms. 1 milliamp meter, 50 ohms. So the 100 milliamp meter probably has a, IM equal to maybe a half ohm. It's a lower resistance meter. The more current it takes to swing it up to full scale, the less resistance it's gonna have, because it ain't gonna take as many turns on that coil to get the required torque. Now the meter is going to have polarity readings in it. We'll draw a little bit of a meter needle there. It's going to have polarity markings on it. And basically these polarity markings, you hook them up so that the negative is closest to the negative supply and the positive is closest to the positive supply. If you hook it up wrong, the needle will deflect backwards, and depending on how much current and the durability of your meter, it isn't impossible to damage it. We're going to put our polarities on each of our resistors too. We didn't put them on there yet, but we're going to put them on there now. Negative, positive, negative, positive, negative. And you'll see that this meter, the polarity in this current measuring application, the polarity of the meter goes in just like the polarity of any other load. Now, let's see here. We've put a 100 milliamp meter. We've connected the polarity in as we properly. And the meter's rated at 100 milliamps. And meters can be rated in milliamps. They can be rated in amps. They can be rated in microamps. And we need a low resistance to a current meter. We have RT here. Let's put the RT down. We calculated that before, but 250, 250, 250. We have 750 ohms. So we probably desire a resistance of the meter of no more than 1/100th of that, but 1/100th of 750 times 1/100th is 0.75 ohms. And we're based on the typical values we looked at, we're guessing that our 100 milliamp meters probably got about a half an ohm, or maybe even less, which is 0.5 ohms, which is definitely less than that. So it's a suitable meter for this job. Now, let's think about what would happen when a meter has too high of a resistance. We're gonna draw another circuit down here. So we have a circuit here. We have a very low voltage on this circuit. Voltage is 0.25 volts. And we have a resistor in here equal to 2,000 ohms or 2K ohms. And I'll put some polarities on here too. And this works out to 125 microamps. This is a very low voltage, small resistance. This is a circuit that we could have some problems with. If we put a 50 microamp meter in here, 50 microamp. And we have 2000 ohm IRM, the resistance of the meter, equal to 2000 ohms. What's going to happen here? Instead of having 2,000 ohms in our circuit, we've now got 4,000 ohms in our circuit, and that's going to change our current greatly. That's going to go from 125 milliamps to about 62.5 milliamps, or microamps, excuse me. Now, I'll let this be a 100 microamp meter. Let's say it's a 200 microamp meter. Let's say it's still got the 2,000 ohms of resistance. But this resistance, which was large compared to the total resistance of the circuit, really changed our value, so we don't really get to see what's going on in the circuit when the meter's not in there, and that is not helpful for figuring out what's wrong with a meter or what's wrong with a circuit. So we have to have a more sensitive meter to read these really low currents where you don't have very high resistances. And what we would probably have to read something like that, we could have a couple choices. We could read the voltage across the resistor and calculate the current, or we may have a meter with a amplifier sort of thing on the front end of it, rather than just a simple meter movement like we've been talking about, which would allow us to read these really low current levels in these low resistance circuits without disrupting the resistance and the current of the circuit. Now, a meter, you don't find a meter movement in every possible range. So if you need a different range, you might be working with what's called a shunt on your meter. And how does a shunt work? We've done a lot of talk about parallel current divisions. So basically, when you put a shunt on a meter, we'll put our little voltage supply here, and we're going to put some resistance. We don't know what it is. We'll just assume for right now it's high in relationship to the resistance of our meter, so we're not messing up our reading by putting a meter in a circuit. We have I equal to 5 milliamps. Here's our circuit rolling along, I equal to 5 milliamps. Now we want to add a meter to that thing. We want to actually measure that current. So put the meter here. Well, I want to draw that. Yeah. We'll put the meter right here, the meter movement. We don't have a 5 milliamp meter movement. We only have a 1 milliamp. I am the current full scale deflection of the meter, 1 milliamp. And we're also going to need the resistance of the meter, so we'll put that here. Resistance of the meter equals 50 ohms for this particular 1 milliamp meter movement that we're using. So we connect our current here. Well, we're 5 milliamps. It's a 1 milliamp meter, so we're going to slam that needle all the way to the right against the peg. So what we do, we add what's called a shunt resistor. Resistor in parallel or in shunt with the meter. So some of the current goes to the meter and some of the current goes through the resistor. So we will have two currents now. We will have IM, which is going through the meter, and we will have I shunt, which is going through the shunt, and we'll call this resistor RS, R shunt. And we've talked a lot about how voltage or current divides in a parallel circuits. And what will happen, this whole thing will be all contained within your meter case. You won't, it'll be pre-done, but that's how they do it. Now suppose we want to read 5 milliamps with a 1 milliamp meter. Well, let's think. First of all, because it's parallel branches, the voltage across each branch is equal, so when you double the voltage, the current through each one will double. So the currents through the meter and the current through the shunt resistor will remain proportional to each other. So what we want to do is we want to have 5 milliamps through the whole circuit, deflect the meter all the way to the right. So we need to have a current through the meter. We want our meter current, we're going to our IT, which is our total here, this is IT, is going to be equal to IS plus IM. Now, this is our current summation formula through parallel branches that we've looked at many times. We know IT, it's 5 milliamps. We don't know IS yet. We do know IM because it's a 1 milliamp meter movement, and that's what 1 milliamp will run that needle all the way to the peg, full scale deflection. And we want that to happen when we have 5 milliamps. So we want full scale deflection. So we'll have 1 milliamp here. So what is IS, the current through the resistor? Well, we subtract 1 milliamp from both sides. We have 4 milliamps for IS. So let's write that here. Let's write 1 milliamp here through the meter. And let's write 4 milliamps here through IS, through the shunt resistor. Well, we have the current. We don't know the resistance. And we don't know the voltage, but we have a formula, Ohm's law. Voltage, or current, excuse me, resistance equals voltage divided by current. We have the current, 4 milliamps. We want to know what value of resistor for RS. So we need the voltage too. Well, we have another formula that voltage equals I times R. Now we can utilize that to find out the voltage when we have full scale deflection on the meter, because we know that the resistance of the meter is 50 ohms. We know that the full scale deflection is 1 milliamp. So voltage of the meter, this would be the meter voltage across that meter at full scale deflection. Well, that's going to be, we're going to use this here, I times R. We're going to use IM. IM, the rating of the meter, equals IM, and we're going to multiply times RM. Let's make this a lowercase. RM. Okay. So if we know the rating of the meter, 1 milliamp, we know the meter is full scale deflection, we know the resistance of the meter, which is the resistance of the coil, which basically doesn't change, not significantly. Temperature could change a little bit, but not meaningfully for our purposes here. So we'll substitute those values in. IM, 1 milliamp. The resistance of the meter was 50 ohms. Well, that ends up being 50 ohms times 1 milliamp ends up being 0.05 5 volts. So now we know what the voltage across the meter, the voltage drop across the meter is when we have our 5 milliamps, well actually our 1 milliamp going through the meter movement. We want to find a resistor that will allow 4 milliamps when we have this voltage. So RS will be equal to, we'll substitute, say just V, we use VM, the voltage of the meter, and the full scale deflection current of the meter, which is 1 milliamp, and when we multiply that all out, divide that all out, we put our 0.05, and we're going to divide that by 1 times 10 to the third, 10 to the minus third. No, we don't have 1 milliamp. We want 4 milliamps. 1 milliamp is the meter, but we have 4 milliamps flowing through the shunt resistor. So that's 4 times 10 to the minus third. Anyway, if we work that out, that comes to 12.5 ohms. So we need RS, I'll write that over here, RS equal to 12.5 ohms. So now we have 12.5 ohms here, 50 ohms here. We have 1 milliamp there, we have 4 milliamps there. You'll notice that 12.5 is also 1/4 of 50. So the same voltage is going to put 4 times as much current through the resistor. And now we've taken our 1 milliamp meter movement and we've turned it into a 5 milliamp meter, which we can use for measuring currents up to 5 milliamps. So let's review the rules which we used here to do this. How you calculate a shunt resistor. We have to first calculate we have two things. We got to calculate the voltage of the meter, and we got to calculate the current through the shunt, which we can do in either order. No, we do. Yeah, we can do it in either order. So we had the voltage of the meter, VM, equal to IM, the full scale current of the meter, times RM, the resistance of the meter. And then so that was just our voltage equals current times resistance. Now, we also had to calculate the current through the shunt. And this is our current summation formula. We have IT equals IM plus IS. Well, and that's just our current summation formula. Let's solve that for IS because we want the current to the shunt. So we're going to subtract IM from both sides. Minus IM, minus IM. So what we end up with is IS, the current to the shunt, equals the current total minus the current to the meter. Which that makes sense. The current to the shunt, total current in, take away what goes here, what's left here, we have what's left here. And then we basically use VM, let's use a different color here. We use VM, we use IS, and we use the formula that resistance equals voltage over current. We do some substitution. Well, it's not really. We use VMVS, and we're looking for RS, so we can add subscripts to this, and we end up with the resistance of the shunt is equal to the voltage of the meter divided by the current of the meter. So we now have a formula for calculating the required shunt resistance. Now, if we have a meter we have a 50 microamp meter movement. And we want to extend that, we want to use it to measure 5 milliamps. We're going to need a shunt. We're not going to calculate the shunt at the moment. We're going to figure out how much current will be through the shunt. So what is the current? What is shunt current? We'll call it IS, the shunt current. Well, we got this formula here. We have IS is equal to IS is equal to the current total, which we want to be able to measure 5 milliamps, but 5 milliamps is also 5,000 microamps. Let's put 5,000, let's convert that to 5,000 microamps. Let's put that right here too, so you microamps. And we want to subtract from that the meter, which our meter is a 50 microamp movement. And you can see why I switched to microamps here, because you need the same units for subtracting for it to work out. So 5,000 minus 50 is 4,950 microamps. So if we want to measure 5 milliamps or 5,000 microamps using a 50 microamp movement, we need to divert at 5 milliamps, we need to, or 5,000 microamps, we need to divert 4,950 microamps or 4.95 milliamps through the resistance, or through the shunt resistor, in order to use that more sensitive meter to measure that greater amount of current. We're going to do another little talk about that. Now we were not given a value for VM. We would need, if we were given a value for VM or for RM, we could calculate, if we had RM, we could calculate VM. We could do the VM over IS and get the resistance of the shunt, but we don't have that. If we were given VM directly, we could just go VM divided by the current through the shunt and go directly to the resistance value. But we don't have that information, so this is as far as we can go with this problem, but we do know how much current we would need to put through the shunt. Well, let's change these values here to match what we just did. See, we'd have 50 microamps, and we would have 4,950 microamps, and this is still 5 milliamps. But you notice that we got to divert a lot more current when we use a more sensitive meter to extend the current range up like that. And we're going to do another one here. We're going to be given some different information here. We're given RM, which is equal to 1,000 ohms. We're given IM, which equals 50 microamps. And now we want to have our range from 50 microamps. Said we want to be able to do 1 milliamp range. Range needed 1 milliamp, which is equal to 1,000 microamps. And again, we want to get that in the same terms. So we need to calculate first the current through the shunt. Remember, we had the formula that IS equals IT minus IS, right? And we want to, IS IT minus IM. IT minus what goes to the meter, leaves what goes to the shunt. So we're going to do that here. We're looking for IS. We have IT given to us, which we're wanting to measure. We're wanting to measure 1 milliamp or 1,000 microamps. And we want to subtract from that the current to the meter, which we're given. This is a full scale deflection. We're setting it up to get a 1 milliamp meter to work or a 50 microamp meter to work for a 1 milliamp measurement. So we're going to subtract from there 50 microamps, and that leaves 950 microamps for RS. Now we're given IM and we were given RM. So VM, we're looking now. We're going to use the formula for Ohm's law that says voltage or resistance equals voltage divided by current. Or in our case, we're looking for RS. We're looking for RS. Then we're going to do the voltage of the meter divided by the current of the meter. Well, we weren't given the voltage of the meter directly, but we have this formula, current of the meter times RM. So we can say that RS, we want to get the voltage of the meter at the top. We have a formula for that, equals IM plus times RM. IM times RM. The current of the meter times resistance of the meter. We're going to divide that by, the current. No. We want IS here. We want IS. The resistance of the shunt is the voltage of the meter divided by the current through the shunt. So here we've got the voltage of the meter, the current through the meter times the resistance of the meter. We're going to divide that by the current through the shunt, IS. Now we have these pieces. We have IM, 50 microamps. We have RM, 1,000 ohms. And we have IS, which we calculated here to be 950 microamps. Anyway, when we work this all out, it's going to 50 over 950 is a little bit greater than a 20th. When we work this all out in the calculator, we end up with 52.6 ohms. So for this particular application that we just did, we needed RS equal to 52.6 ohms. So that would allow us to convert our 50 microamp meter movement into a 5 milliamp meter. We had 5 milliamps going in, 50 microamps going through the meter, 950 milliamps going through the shunt resistor. We had 1,000 ohm meter resistance and a 50 microamp meter movement, and we used basically our voltage drop, V equals I times R, I being 50 microamps, R being 1,000 ohms, to get us an expression that represents the voltage across the meter. And we divided that using this resistance equals voltage divided by current. We divided that by the current we need to the meter. We end up with 52.6 ohm shunt resistor needed across this 50 microamp meter movement to use it as a 5 milliamp range current meter. Anyway, that's probably enough for today. Be sure to like and subscribe. Thanks for coming back. And until the next time, keep on learning.